Hello, everyone, and welcome to this presentation. My name is Erik Österlund, and I'm a consulting member of technical staff in the Java platform group at Oracle. So today I'm going to talk about ZGC, and that's what I've been tinkering with for the last 6 years or so. And yeah, I've been mostly working on low latency garbage collection, and even before joining Oracle, I was doing a PhD in that. So that's kind of been my focus. And I think that we're about to bring low latency GC to the next level. But first, let's talk a little bit about what is ZGC. ZGC is a scalable low latency garbage collector. What that means essentially from the user point of view is that you no longer need to think about GC pauses. And the goals have been for a long time now to scale to terabyte size heaps while having a very low latency. We're targeting sub-millisecond GC pause times. And we want all of this to be as simple as possible to use. So we have a bunch of auto-tuning to make the configuration as small as possible. In terms of availability, ZGC is available on a wide range of platforms at the moment, including, of course, all the Oracle supported platforms. But we also have a few bonus ones, such as Linux, PowerPC, and RISC-V. So now you're thinking, this all sounds great, but is there any catch? Well, we do have a producer-consumer problem where essentially the garbage collector is producing free memory, and the application, when it allocates memory, is consuming free memory. And there is a bit of a race where if the allocations are outpacing the garbage collector, then we end up in a situation that we call an allocation stall. And it might look something like this in your GC log. Here we can see that we have two threads that stalled, and this happened because they were allocating memory faster than the GC could free memory. So the main way of working around this is to increase the heap size. By increasing the heap size, you give the garbage collector more time to free up memory. There are some other things you can do as well, such as increasing the number of concurrent GC threads to collect collect the memory faster. But in general, there are some workloads where there are large object graphs and high allocation rates, and then the application will probably outpace the GC, despite having some tricks to reclaim memory faster, and it's as fast as it can be. And this leads us to what we are working on at the moment. It's a new version of ZGC that we call generational ZGC, where we try to do even better. The main thing we're trying to exploit here is the generational hypothesis. It's a very common pattern in Java applications that we are exploiting, that objects are typically short-lived, which means that most of the garbage is among young objects. So the way we're going to do this is that we're going to split the heap into two separate sections that we call generations, a young generation and an old generation. And when the application allocates new objects, they will be placed in the young generation initially. And after it's been a while, then it might get promoted to the old generation. And what we can do now is to focus garbage collection in the young generation without tracing through the old generation. And the hope is that by doing this, we will be able to withstand higher allocation rates and lower the heap headroom and also lower the CPU usage of the garbage collector. And I said that we're splitting the heap in two. However, it's worth pointing out that it's not going to be a contiguous virtual address space like this picture. Instead, ZGC uses a discontiguous memory layout that looks a bit more like this. Each one of these little squares is called a region, and a region can be old, it can be young, or it can be just free memory, but it's completely discontiguous, and this helps us fight fragmentation among larger objects in a pretty neat way. Now, when we're collecting garbage in a generation, we'll go through a number of different phases, and the details look slightly different depending which of the generations we are collecting, but the general picture looks something like this. We have these orange arrows pointing down. They are GC save points. What they have in common is that they're synchronization points and don't really do much of anything worth noticing. But then we have the horizontal arrows that are concurrent phases. Let's walk through these in a bit more detail. So if we're collecting a generation, we would start with the mark start pause. And this is, again, just a synchronization point to make sure all the threads know that we're marking. Once we start running again, we start the concurrent mark and remap phase. And it does look a little bit different for young versus old generations, but the main idea is that we're tracing through all the objects that are live in a generation. And at the same time, we're remapping pointers from a previous GC cycle. Then once marking has concluded, we perform a mark end pause, a synchronization point to conclude the marking. Once that's done, we start a concurrent prepare for relocation phase, where we're trying to figure out which objects we should move around to free up memory. Once we've finished figuring that out, we go on to the relocate start pause. And this is a synchronization point for starting moving around objects, which is exactly what we're going to do next in the concurrent relocation phase. We move objects out from regions and free up the free memory of those regions. Now, these generations can be collected concurrently and in parallel. By concurrent, I mean that each generation collection is running concurrently to the application threads. However, they're also running concurrently to each other. So as you can see in this picture, you can run the young GC at the same time as the old GC. And within each of these generation collections, we're utilizing multiple threads, hence the parallel part. And hence why this is both concurrent and parallel. The main way that the garbage collector is collecting garbage is through minor and major collections. If we start with the minor collection, the minor collection wants to collect garbage in the young generation only. So it's not going to trace through the old generation at all. And I did say that there are some details that vary depending on what generation we're collecting. This is one of those instances where you see we start tracing through the roots, and the roots in this case is the normal global roots and thread roots. But we also have a data structure called a remember set. This tracks the locations in the old generation where we might come across pointers into the young generation. These are also roots to the young generation. So we use these roots to trace through all the live objects in the young generation. And once we have computed that, we know what objects are garbage. and we recycle the memory. Now, if we look at major collections, they want to collect the entire heap. And the way that this is done is to start with a young generation collection. And similar to before, we have our normal roots plus the remember set that we use to trace through the young generation. The difference here is that while we're tracing through the young generation, we're also remembering all the pointers into the old generation, which become the root set into the old generation. And that allows us to trace all the live objects in the old generation. And once we have finished doing that, we know what objects are garbage in the old generation, and we can reclaim memory. I mentioned that we found automatic tuning to be a very, very important thing. And this is no less true in the generational version of ZGC. In fact, if we start looking at, for example, how large the generation should be, we did not want to introduce an XMN flag to specify how large the young generation should be. In fact, our generations do not have a capacity. At any point in time, you can know how much memory are currently in a generation, but they don't have a capacity in the same way as some other collectors. And that means that the free memory is available for either generation. And therefore, we don't need any generation sizing at all, which is one flag less to care about. Another thing that you could possibly specify is a tenuring threshold, but once again, we don't really want people to have to specify it to do it automatically. Now, I should probably mention what is the tenuring threshold. Is essentially the threshold after how many young collections we decide to promote objects to the old generation. And how this should be set is rather complicated to know as a user, because it kind of depends on the ratio of the live residency in the young versus old generation. If you have a very large old generation, then you might want to tenure less, because triggering old collections is going to be very expensive, and vice versa. But we have a bunch of calculations that automatically calculate how much memory it should promote. And therefore, you don't need to care about it at all, which is quite nice. Another one of these tricky heuristics problem is, when should we start an old generation collection? And of course, as a GC designer, it's tempting to just throw in another JVM flag and have the user specify this for us. But it is rather tricky to know how to set this flag correctly. So instead, we are calculating all of this automatically. It's essentially comparing the cost of when young GCs are becoming much cheaper if we would have freed a bunch of memory in the old generation, so that the frequency of young generation collections can go down, and calculate the break-even point where when it becomes worthwhile to perform an old GC to make the young GCs cheaper. Fairly tricky, but once again, nothing that the user has to deal with, which is pretty nice. Another one of these interesting problems is how many GC threads should we use? And we don't need to specify this either. In fact, this is an area where we already had some automatic stuff in the mainline version of ZGC. But we're taking this to the next level now, in the sense that we can now also change the number of GC threads dynamically while the GC is running. This is something we couldn't previously do. So we could end up in a situation where we select, let's say, 4 threads. but suddenly the application starts allocating at a much faster rate while we are performing GC. Previously, we were unable to do much about that, and you might end up with an allocation stall. Whereas now we're continuously monitoring the application while it's running and react to such changes so that we can increase the number of GC threads automatically and avoid allocation stalls. So this is also becoming much better. Now, then you might wonder, so what should I set then? Good question. And at the moment, the only thing you really need to specify is the max heap size. And having said that, we have some thoughts about maybe figuring this out automatically too, but we're not quite there yet. So at the moment, specifying a heap size is what you gotta do. Now, you might be wondering, how does this stuff work under the hood? Please let me know. In order to understand that, we should start by looking at colored pointers. This is a core design concept in ZGC, and we'll start looking at the mainline version of ZGC. The way that we encode metadata is in the 4 high-order bits here, the addressable memory, and we're encoding it as multi-mapped memory. What this means is that each one of these bits has an extra virtual mapping to the same underlying physical memory. And this is a trick that allows us to encode some information in the pointers, and that allows us to do a bunch of stuff concurrently. And this is enabled with something that we call a load barrier. The load barrier is a piece of machine code injected by the just-in-time compiler wherever we have reference loads from the heap. What the load barrier does is to check if the pointer colors are bad. If they are bad, we take some action and heal the pointer. Otherwise, we keep on running like normal. And it's worth mentioning that a typical profile of many applications is to have approximately 80% loads and 20% stores. Because of this, the performance of the load barriers is rather crucial because that is the most frequently executed barrier. And with the multi-mapped memory, we're able to have a 2-instruction load barrier, which was very nice. However, the situation with generational ZGC is a bit more complicated because the algorithm is more complicated. And we currently end up in a situation where we need 12 color bits. And as you can imagine, we can't really feasibly multi-map memory this many times. So what are we going to do? The solution is something that we call colorless routes. And the main idea here is that the load barriers will also remove the colors so that we only have the address bits left as part of its work, as well as, of course, checking if the pointer is bad. Instead, these colors that we removed are restored when we store a pointer back into the Java heap. And by doing things this way, we don't need multi-mapped memory anymore. The challenge, as you can imagine, is how do we retain this 2-instruction load barrier without using multi-map memory? Because we have to do one more thing, which is to remove the color bits. How can we do this with the same number of instructions? It's a very long story and kind of tricky, but I will at least show you the result of it so you can see that indeed there are only 2 instructions. So here is some x86-64 assembly, and on the left-hand side in the green, you see test and branch. That's the normal load barrier you have in mainline ZGC. And you see on the right-hand side, a shift and branch with generational ZGC, also 2 instructions. The shift obviously removes the color bits, And somehow that's all we need to do to figure out if we should take a slow path. The shift itself is updated with cross-modifying code. However, how this works in detail, I think, is beyond the scope of this presentation. But at least you can see that there are only 2 instructions there. So the layout of the colored pointers in generational ZGC look slightly different. You see the low order bits here that we shift out. That's where we have the colors. And yeah, most of the rest is the addressable memory. And it's worth noting that there's more addressable memory than we had before. We used to have 16 terabyte addressable memory. Now we have 64 terabyte addressable memory. So that looks nice. And when we have removed the colors, we're left with the addressable memory and some unused bits. I should also mention that we can scale up the addressable memory to 128 terabytes now. One of the bits is always a 1. It doesn't need to be, but we'll see if anyone needs that kind of Java heap. So let's talk about some of the benefits with colorless routes. We saw that we could have a larger addressable heap than ever before. We also saw that we could have more colors than ever before. I should also point out that there's been a particular bookkeeping problem that some users have run into, where there's a difference between RSS and PSS when tracking how much memory the process is using. And sometimes people come to us and say, it looks like you're using way more memory than everybody else. And in fact, it's because the RSS value is accounting multi-map memory multiple times, whereas the PSS value does not. However, it seems like a lot of the tools in the tool chain are using RSS, so it will definitely be nice to not have that problem anymore. And as we could see, we still have a 2 instruction load barrier, and this holds true on x86-64 and AR64. And this despite doing more work. So let's talk a little bit about the store barrier then. The store barrier is a piece of machine code injected by the just-in-time compiler when storing an object reference to the heap. And what this does is to check if this field is the first field right since some GC shift earlier. And if so, we take some action. And as well as performing this check, we also make sure to color the pointer that was colorless before storing it into the Java heap. Now, these actions that we can take in the slow path are partially dealing with concurrent marking in the young generation, concurrent marking in the old generation, as well as remember sets maintenance. Just for fun, we can also see what the actual instructions look like in x86-64. And the main point of this is you can see that it's a conditional branch to check is this the first write, and then 2 instructions to color the pointer. So altogether 4 instructions in the fast path, which is pretty good. And now you're wondering why are we doing all this stuff? Clearly we need 4 more instructions in the store barrier. So if that's all there is to it, this move is questionable. So to answer this question, we've run some benchmarks, and in this case, we tried out Cassandra 4, and we have a benchmark setup where you run Cassandra 4 with 128 gigabyte heap, and you can configure a request rate. What we did is to check how many requests can we throw at this system before we get an allocation stall. And this is the result. As you can see, with generational ZGC, we can increase the request rate about 4 times as high before running into allocation stalls. And if we look at the memory aspect, we also notice here that we can also reduce the size of the heap to approximately 25% of what the original ZGC algorithm used, and still not run into any allocation stalls. So both of these things are achievable at the same time, which means in essence that we're getting 4 times high throughput while using 25% of the memory, and all of this while retaining the sub-millisecond GC pauses. So in a way, I guess you can say that we're doing the same stuff that we did before, but with less hardware resources. Now, if you would like to have more information, we do have a wiki page where you can find out more. It's wiki.openjdk.java.net/display/ZGC. And there you have a number of interesting things you can read about, including some tuning that is getting smaller and smaller, but there are some tricks there that you might want to look into if you want super high performance, and some tricks. And if you want to reach me, then, well, I'm Erik Österlund, and you can reach me on this email address. And you also have my Twitter and my GitHub account. And yeah, that was it for me. Thank you very much for watching.